Hello. How are you, everyone? Better than I deserve. Thank you for asking, Alicia. Finally, we got your grades up and running. I am terribly sorry for the inexcusable delay. Okay, will not happen again. Blame the essay questions. And this is a summary of the scores. The average score was 78%, which is higher than my previous years. On average, I would get 67, 68%, the average score. Last year, we had a similar exam on Canvas. The average was around 72%. So I'm very happy with this average score. The high score is 100%. The low score was 35. What's interesting about this histogram is that there's one mode, there's one peak, okay, which is, personally, I think it's very good news, because typically what we get in classes, first, second year classes, you get a bimodal distribution, and that kind of separates the class into, those average and above and those kind of trailing behind. This is good news. I think that it seems that, I think it's a quantitative indication that overall, as the years pass by, the course matures, you're all coming in with more background potentially in Python, etc. So it's kind of moving the class to a unimodal distribution. The standard deviation is 14. So now going back to regression, if we were to consider the mean value to be representative of the data, then the standard deviation tells us the error we've committed in using the mean to represent all of those data. So on average, everyone is, about 14 points away from the mean value. That's kind of what we get on average. The average time was 20 minutes to complete the exam. So, that's close to the 30 minutes, but I think it's good to give you 1 hour on exam 2 and moving forward. So you'll get your 1 hour next Thursday with the 2 attempts. If you would like to contest your grades, so both attempts were graded separately, and we took the highest grade. We didn't grade questions across attempts because you were getting different questions per attempt. Okay, so we took the highest grade of either attempt. Okay. If you want to contest your grade, there's something, I tried to put as many comments as I can. Some duplicate questions, I put the comment on the first attempt or on the second attempt. So make sure you look at both attempts to see if I provided you with a comment. If that's still not clear, if you disagree, just shoot us an email, and we'll essentially put you in the queue for contesting your grade. You have until Saturday midnight, okay, to contest your grade, just like is stated in the syllabus, and yep, hopefully, exam 2, now you get an idea of how these exams are going to be like. There's definitely going to be less essay questions on exam 2, okay? Okay, so I'm going to get back to nonlinear equations. Last time, we covered the bisection method, which is the kind of the simplest, no-brainer way of finding a root. You say, okay, my root is somewhere here between 1 and 2, or between 5 and 7, between -3 and 0, right? So take that bracket and cut it in half and check if that half point makes the function go to 0 or not, or less than your tolerance or not, and then continue. Keep shrinking your bracket until you home in on the root. That was the description of the bisection method. We did an example by hand, and this is just a reminder of what it needs, how the method works. kind of an algorithm description. Okay. So now we're going to go and do this in Python. We did this example by hand last time. Okay, so now we're going to Pythonify this, turn it into Python code. And I will start by asking you a question, a group question, please. Go ahead and start talking. Put your name tags in front. If you were to write a Python code that implements the bisection method, okay, so that's a function that I'm going to call, implements the bisection method, what would you choose as inputs and as outputs for that bisection routine? Okay. Give it some thought. Yeah. Kimball, Kara, do you want to join forces? If you want. Okay. So I always forget your name. I know you're Tata. Michael. Michael. And you don't put your name tag, but you, that's okay. That's okay. Michael. I remember. Okay. It's hard. And like last time you didn't have your mask on, I was like, who is this person? No, it's good to know. Names on the masks or like on the, yeah, on the laptop. So I know you're Anna, Lizzie, right? Alex. Okay. Okay. See, I'm starting to remember. All right. You're right on time for a good question. A and B, final answer. You never came to student hours yesterday. On Tuesday, you had something going on with the code, and you just. The TA's office hours on accident instead. And yeah, it's working now. Yeah, okay, perfect. Good to know. I was like, yeah. I got it. Okay. 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 Good to know. All right. So do we have any answers? Let's start with that section of the class. Who would like to start kind of volunteering? Go ahead, Michael.
You need some sort of data that you're trying to find the root of or a function.
Okay, so you need a function. Okay, we're not going to deal with discrete data. We're going to deal with, because it's a much different problem. So we need the function or the residual function specifically, right? Yeah. So we need the residual function. Okay. What else? Let's see this side. Rich. Okay. So you gave it all. Okay, so Rich gave us the rest of the answer. So Michael said we need the residual function. So that's just a Python function name. Okay, it takes a x value and returns a function value, right? So it could be exponential x or cosine x minus 1, etc. That's the residual function. So we need that. We need the interval, the initial interval, a and b. And you better make sure that that interval brackets the root. Okay, we'll think of ways of how we can make sure we bracket the root. We need a maximum number of iterations. Like why would we need a maximum number of iterations? Kevin? Yep. Yep. If your bracket was off, right, you're never gonna get to iterations. You're gonna keep dividing by half to infinity, right? So a maximum iteration guarantees that your code is gonna stop. Okay, and then you could throw an error, say, oh, maximum iteration reached, and I couldn't find a root, for example. And we need a tolerance, because the tolerance is gonna tell us essentially when to stop, because you might stop at 5 iterations, right? Or 20 iterations, right? So that gives you your tolerance, how close you want that residual function to be, how close you want it to be to 0. Okay. We didn't speak of output. Okay. We didn't say anything about outputs. What would the function return? You want the root? Obviously, the root. That's kind of, at least you need to return the root, right? What else could we return, just for fun? You know, Michael?
Well, if you set tolerance, you could set how many iterations.
Yes, so kind of how many iterations it took you. Yeah. The approximate error. Yeah, good. That's a good point. And how would you measure your approximate error? Iteration. Yep. So you keep a track of your approximate error. All right. So this is what I have here as answers, suggestions. And, there's no one way of doing this, but generally there's, good practices, right? So and at a minimum information that you need, but you can expand your code and make it do whatever you want, right? But like I said, like we agreed, you need the residual function, the initial root bracket, the tolerance, and maximum number of iterations. You return the root itself, an approximate error, or the tolerance itself, where f of the root itself, that is going to give you an error, right? Because it's going to tell you how close you are to the root. It's going to be less than your tolerance anyway, and the iteration count that you needed. Okay. Here is the code given to you. Now I know, over the years I used to ask this as a homework assignment, and everyone would get lost in trying to write the code rather than using the code to actually find roots. Our objective is to use programming for an end goal, which is to find the roots of functions. So I'm providing you with these routines. As a convenience, you're welcome to use them as is, and you can study them as well if you feel like you want to take this challenge on. By all means, don't look at my code, create your own code, okay, and use it and verify it. And that's a great thing, okay? But I'm not holding you accountable to write this code. I'm holding you accountable to how to use this code to find answers. So let's go over it quickly. I called my function bisect. Okay, define bisect, and I take f, a, b, tol, and max iter. F is my residual function. I should have used r to be consistent with the slides. Forgive me for that, but maybe I'll change it right now actually to r. R as your residual function. Okay. So r is your residual function. A and b are your brackets. So we agreed that a should be to the left of the root, b should be to the right of the root, but they might not bracket a root, and then this code is not going to converge. And then a tolerance, maximum iteration. Okay, so first I start by defining a very high error value. Okay, just to start off my while loop. So I take error equal tolerance plus 100, or you can multiply it by 1,000 if you want. It's just an initial value to make sure we are starting with a very high error, so we can enter a loop. We can enter the loop because we're going to use a while loop. And then I put in an iteration counter because I would like to return the number of iterations that it's taken us to get this code done. And notice this while loop. We've seen this before in one of the previous, I think, the Taylor series. As long as my error is greater than the tolerance. Okay, so that's why I started with error equal tolerance plus 500 to make sure my initial error value is greater than the tolerance. Okay, and as long as my number of iterations, my counter, is less than the maximum number of iterations, do something. First, I'm going to increment my iteration counter. Then I'm going to make a guess for the root, which is c equal a plus b over 2. And then I'm going to check if r of a times r of c is negative, then b is equal to c. Okay, so then c is to the right side of the root. Otherwise, C is to the left side of the root. So I recasted B and A, so that I shrink my interval. And now I compute my error equal absolute value of R of C. Okay. Now this error is now updated as R of C, and that gives me a new fresh value. And then goes again. If it is still greater than tolerance, we're going to repeat. It's going to keep repeating as long as this error is greater than the tolerance and n less than max iterations. And once you're done, it's automatically going to exit the loop. And then it's going to return C, which is the root, the latest value of the root, C, and error, and the number of iterations. Okay. Now, we need one more thing. I noticed, I'm going to go back. I'm going to have to mention this. So there was a question in the exam. You probably, all of you got it. It's list 2 ways that you can verify your TDM, your Tomas algorithm implementation. Okay. Verification means making sure that your code is returning the correct answer. It is working as it is intended to do. Okay. Some of the answers were, I would make sure that the matrix is tridiagonal. Sure, but that's not verification. Making sure that the matrix is tridiagonal is making sure that you're catching any misuse of your code. But it doesn't verify that your code is actually returning the correct answer. We mentioned in class that to verify your code for the Tomas algorithm, I would compare with a solution by hand, for example, or I would compare with a built-in solver that I know has been verified independently, like the ones in NumPy, numpy.solve, or using the A inverse. So similarly here, we need to kind of verify that we are getting a reasonable answer. I mean, clearly one verification is that the error, that we found a root, that the error is getting below the tolerance. But it would be also nice to use a very robust method that is out there, like a prepackaged method. And that comes from Python, from the package scipy optimize. So within scipy.optimize, you can import fsolve. I think Kimball mentioned that the other day. Fsolve is function solve. Essentially, it finds the root of any function, a single valued function. Okay. And the way you use it, you call fsolve, you give it your residual function and simply an initial guess. We're going to learn the mechanics of what goes inside fsolve. It uses the Newton-Raphson method. We'll worry about that in a couple of lectures. But for now, we're going to need this to kind of double check if our bisection routine implementation is giving us a reasonable answer. Okay. So let's go ahead and spin up our Jupyter notebooks. There's a notebook under the nonlinear solvers and nonlinear methods module, on Canvas, called Parachutist Example with Gaps. Okay. And so go ahead and load it up, and we'll go and do the bisection algorithm to find the drag coefficient for a parachutist of 70 kilograms, reaching a speed of 40 meters per second after 10 seconds, right? Yeah. So what kind of drag do you need on that parachute? Suppose you're delivering a load to Mars, or to some territory. You want to make sure that that load reaches that kind of speed after 10 seconds of deployment. So how do you design your parachute? What drag coefficient does that parachute need to have? Okay. Now, let's see, is this good enough? Yeah. Everyone have the notebook in front of them? Okay, thank you. All right. So we import the boilerplate, and this is a description of the problem. with our residual function, R of X. Remember last time we defined R of X was, or R of C was mg over C into, it's actually a typo, this should be R of C. R of C is defined as mg over C into 1 minus e to the minus C over mt minus u of t, okay? So our objective is given m, g, of course, and t and u, find the drag coefficient, okay? So again, to rephrase the problem, if you wanted to deploy a certain load and you want to make sure that that load does not descend so fast because it has on it some expensive equipment, for example, then the single thing you can control in the parachute is its drag coefficient. How fast is it going to slow the descent down, okay? So that's why we're interested in C. And then we're going to give it some numbers. For a payload of 70 kilograms, we want it to reach 40 meters per second after 10 seconds of deployment. Okay, so what kind of drag coefficient do we need? And this is what we're after. Okay, so first we're going to define the residual function, okay, for the parachutist or the payload. And I define this simply as R of C, okay? And this function just returns a value. It takes the value of C and then returns a result, because we're going to keep substituting our guess for the root, substituting it in here until this result becomes essentially 0, okay, or less than the tolerance, okay? Okay, so now note here that this residual function has other parameters. I'm not going to call them variables. I'm going to call them parameters. The difference between parameter and a variable, parameter is something you have control over. Okay, it's something, it's kind of an input as well. Okay, a variable is something like you have no control over. Okay, it varies, but the parameter is something you can control. So in this problem, m, g, t, and u are parameters, even g, because I might be deploying this on Mars, right? So all of those are parameters that you can input, you can specify. So I left them out of the arguments, okay? We will learn later how to pass them as arguments, as additional arguments, but for now, we're not going to worry about that. We're going to fix m0, g, and t0, and etc. as, you know, global variables. We're not going to worry about those, okay? But that's kind of why I put them here as m0 and t0 and u0, because those are kind of specified values that we're going to specify down here, okay? And they're going to be inherited directly after we specify them here. Okay, so this just implements your residual function, okay, and returns a single value. Okay, let's go ahead and execute that. All right, so now I would like to plot that residual function versus the drag coefficient while fixing m0, t0, and u0 and gravity clearly, which was kind of fixed over here at 9.81. Okay, so I don't know what C is. So this is R of C. So clearly I'm plotting R as a function of C. So I'm going to vary the drag coefficient. I'm going to create a linear space for the drag coefficients from 0.1 to 100. And then for these values of mass, time, and velocity, I'm going to plot this. And this is what it does. It's just plt.plot, your drag coefficient x, which is the length space, and then R of x versus x. Okay. So we're going to go ahead and plot it and see what happens. Okay, this is it. Okay, so this is our residual function. Okay, this is our residual function for a fixed. You fix velocities, you fix speed, time, mass, and gravity, and you get this one single curve. And the only route, there's one route for this curve, and that's over here. Right? Because the residual always has a root when R of x equals 0. Okay, so the root is going to be over here, somewhere between, you know, maybe 10 and 20. Right? That gives you kind of visually what your bracket is. Okay. All right. So there's a root somewhere between 10 and 20. Good. Okay. So now I'm defining the bisection method. See the slides. This is exactly the code that we showed in the on the slides, and I'm going to change this to R just for consistency. Okay, you can keep it F, it doesn't matter, but I want to change it to R. Okay, so now find the drag coefficient required for the parachutist. Okay, M0 and T0 have already been defined, and I think U0, I defined it here. So there's no need to redefine it again. So let's call bisect. Okay, go ahead and fill in the blanks. You probably already did because you're always so far ahead of me. Kevin is smiling. What did you get, Kevin? What did you put in there?
10 and 20 is the initial guess.
Okay, so you put in bisect. So what is the signature for bisect? We need R. And then 10, 20, right? 10, 20. 100 100 maximum iterations. All right. So it gave us an answer of a root of, so remember, it's returning root, error, and number of iterations it took to get that root. So a root of 15.23, and then an error less than your tolerance, which is 0.1. So our error is 0.03, and 7 iterations. It did that in 7 iterations. That's pretty cool, right? Pretty nice. Okay. Okay. So now, what if we want to find the drag coefficient for a velocity of 10 meters per second? Okay, so let's see. Do you expect the drag coefficient to be larger or smaller? Okay, for the same parachutist and length of time, a lower velocity means that there should be a lot more drag on the parachutist. We therefore expect a larger drag coefficient. Okay, so what this is saying, in the first example we did, we got drag coefficient of 15, whatever that means, but this is a drag coefficient. Okay, with the correct units, it makes sense in fluid mechanics. And now we're asking, okay, what if we want to slow down the payload to 10 meters per second within 10 seconds? So within 10, to slow it down to 40 meters per second within 10 seconds, it required a drag coefficient of 15. To slow it down more, you would need to really have a higher drag coefficient, right? Because that parachute is going to jump up, it's just going to slow it down significantly. So to reach a speed of 10 meters per second within 10 seconds, we would expect to obtain a much higher drag coefficient. Okay, so let's go ahead and see what happens. We're going to put U0 equal 10. And again, with bisect, I'm going to put R. And let's give it the same, I don't know, the same bracket, because we're shooting in the dark. And that's the problem with the bisection method, with closed domain methods. How do you get your, I don't know where my new drag coefficient is going to be. Is it going to be between 10 and 20, between 10 and 100? Okay, so let's put 10 and 20. Okay, and because I want to illustrate a point, tolerance of 0.1 and 100 iterations. And look at that. It gave me a root of 20. That's the upper bracket, right? And an error of 22, which means it never went below the tolerance, and a maximum iterations of 100. So it consumed all iterations. I'm glad we put 100 iterations, right? If we didn't have any iterations there, it would just lock up your computer. Okay. Okay. So we got nothing really. Most likely, it's because our root is outside that bracket. We picked the wrong bracket. Okay, so maybe we change our bracket. You might say, hey, let's put 10 and 1,000. Okay. Ah, look at that. It nailed it. Okay. Gave us a drag coefficient of 68. Okay, 68 as opposed to 15, with an error less than 0.1, so 0.09 or 0.1, and within 8 iterations. Okay. Now, I don't want to put 10 and 1,000. That's kind of hardly productive, because for this case, it might have worked. But what if you had a problem where, what if you had another root between 10 and 1,000? Okay, that's really Achilles heel of these closed domain methods. You need to first see where the root is to pick your bracket and find it. So let's see where that root is for 10 meters per second. And I'm going to plot x and r of x. Okay, again, you see, That root for the velocity of 10 meters per second is right over here, just around 68. Okay. So now that we've eyeballed it, we can go back and repeat the calculation. We can pick a bracket of 60 and 80, okay, with 0.1 and 100. Kevin kind of locked us into that 0.1 tolerance, so we're gonna take it forever, okay? So, yep, 68.75, you know, it's as close to the root as it can be. We can tighten the tolerance. We probably might want to do that. But, you know, that's how it works. For 0.01 tolerance, 8 iterations, shrink the tolerance. Yep, can't do any better anymore. Okay, so now let's do, so this result direction coefficient, you know, 4.5 times higher than the other one as expected. Now let's use the built-in function fsolve. Still at u0 equal 10 meters per second. So this u0 here is like a global declaration. It's gonna pick it up in that function over there and just use the correct u0. So what you would do with is simply call fsolve, give it the residual function and initial guess. That's really, really nice. Okay, you can give it more options, like a tolerance, etc. But it has a default relative tolerance of, I think, 10 to the minus 10 or minus 8. They keep changing it, but if you call that, gives you 68 point, the number of the beast. 68.666. I've never, this is the first time I see this. 68.666228. Okay, that's actually very interesting. So yeah, and fsolve, very convenient. Now it's really cool to just put a number and just put a residual function in a number. That's kind of the hallmark of what we call open domain methods, and we will learn how fsolve works. Okay, and we'll have our own implementation of a routine that takes in just a single guess, okay, and finds its way to find the root. And you can, fsolve is so great. We can change our conditions. We can go back to the 40 meters per second problem with the same initial guess, gives us the 15, right? It's very, very robust. You can change the payload's mass, so 100 kilograms. Yep. You know, it does its thing. So it does work well. Pardon me? And no questions? Okay. All right. Hey, what do you think? Pretty simple, pretty cool. Okay. Bisection method. Okay, let's make it harder. Okay, so we can switch back to the slides now. If I can find my cursor. Okay. The second closed domain method, we are still within closed domain methods where you need a bracket. The reason I teach those is because they are intuitive about how root finding works. In practice, I've never seen anyone use closed domain methods to find the roots of complicated functions or multidimensional problems. It's nearly impossible, okay? But they're very helpful to visually observe what is going on, especially this method as the precursor to the Newton-Raphson method, okay? This method is called the method of false position or the regula falsi method. Instead of, so with the bisection, we cut the interval in half because as far as we know, the midpoint is as good as any other point. And it's probabilistically the point that, you know, is the best probabilistically chosen point, maximizes what's called, maximizes information entropy. But you could have chosen a third of the interval or 2/3 or, you know, square root of 2 of that and whatever you want, okay? It's up to you. But a more rational basis to do this is this method. And we start similarly with an interval a and b. So in this case, we take that same function. We have a root at around, what is it, 6.7 or something was last time. And we start with an interval a and b. And instead of taking the midpoint between f of a and f of b, we instead draw a straight line, okay, between f of a and f of b. Okay. Now we take the intersection of that straight line with the x-axis, where the root is going to be located. And that intersection point is going to be our new guess for the root. Okay? By section, we took the midpoint halfway. Over here, we connect the function values with a line and intersect that line, okay, with the x-axis. That gives us our new guess C. Okay? So now here's your activity. This line has a slope of f of b minus f of a over b minus a. Okay, now I want you to use that, the equation of a straight line, and find C, find the value of C. So the equation of the straight line is mx plus alpha or beta, right, plus an intercept, right? So find C based on this line, okay? Go ahead, do some math. This is partly a math class, yes. There's yeah, surprise. I mean, we use math, right? I'm not like proving theorems and stuff, you know. Y'all still doing good on Zoom?
Yeah, Professor.
Thank you, Sovit. Yep, write the equation of the line, y equal mx plus beta or something, and then find the intersection of that line with the x-axis. And that gives you the point C. Anyone's got a value for C? It needs to be in terms of A, B, and f of A and f of B exclusively. Okay? Then ask. Yeah.
So I'm not sure I understand this correctly. I set up this linear, like this linear equation, y equals mx plus b. And then I was like trying to solve for B first and then solve for
Yeah,
C.
so you want to solve. So the equation, no, it doesn't have C in it. The equation is a function of X, the entire X-axis, because that line goes over the entire X-axis. Its equation is Y equal mx, this is M, right? Mx plus Q, let's say, because we don't want to use B to confuse nomenclature. And then you need to find the intercept. So that's this number. So how do you find the intercept? You evaluate that function, that straight line at x equals 0 is going to give you C, but you still have that unknown, right? So now you have two unknowns. So instead you evaluate at a point that you know, either A or B, to get the intercept, right? So if you evaluate it at A or at B, then you get that intercept, and then you go evaluate it at 0, okay? Or at C. All right, let's see. Any takers? Any? Saw some progress. Okay. Do you guys have an answer? No? Okay. Maybe let's see what you did. Okay. Oh, that's interesting. You did yeah, and you did f of that's yep, f of b. So you took, because that's the right slope, so b minus c. Yep, that's actually pretty smart. Go work, Ryan. Okay. Okay, so let me show you how I did this. I think many of you kind of followed the same strategy. So this will answer all of your questions. There's a new method that your colleague suggested here, which I think I'll incorporate next year. Thank you. So the line connecting A and B has the formula y equal mx plus q. We know m, okay, that's the slope, f of b minus f of a over b minus a. We do not know the intercept q, okay? M is the slope, like I said. Now the intercept can be found by evaluating that line at either x equal a or x equal b, because we know the value over there, okay? We know the value over there. So for example, if you set x equal b, you have y at b is m times b, which you know m, you know b, you don't know q, but you know f of b. So you have one equation with one unknown, so that gives you the intercept. Q is f of b minus mb, whatever numbers that is. Now finally, the point C is where the line intersects the x-axis, or y of c, right? That's the straight line. Y at c is equal to 0, but that's also equal to mc plus q. You know m, you know q. You solve this equation for c, and now you get c is equal b minus f of b over m. You got, even if you got the signs differently, that's fine. Okay. The other method that your colleague presented, which is easier than what I've done here, is just consider the line, that slope between c and f of b. So f of c and f of b, and you know f of c is 0. So that slope is essentially given to you by evaluating f of b minus f of c over b minus c, and you know what that slope is. That's m, f of b minus f of a over b minus a. So you got your c in one shot. Okay. Okay. So now that, right? So okay, we got our formula for c. Now we determine the same way we did before whether our new guess for the root is to the left of the root or to the right of the root. And we do that by evaluating the product f of a times f of c, or f of b times f of c, whichever one you want. If that product is of the same sign, okay, so if f of a times f of c is positive, then they are both on the same side, either, so then you change, then your root is to the right, and then you update your interval, just like we did with the bisection method. Now you repeat ad infinitum, okay? You draw another straight line. Look how close it's suddenly getting to the root very quickly. It converges in general much faster than the bisection method. And then you continue doing that. You evaluate over and over again. Okay, there's a little bit more algebra involved, a few more function evaluations, but you converge faster. Okay. And this is the algorithm for the regular falsy or the method of false position. Given A and B, which bracket a root of f of x or r of x in residual form, calculate the slope of the line connecting f of A and f of B. So that's m. Then calculate the point at which this line crosses the x-axis. That's your new guess for the root. In the method, in the bisection method, C was A plus B over 2. Okay. Now we have another formula, another recipe for C. Okay, then check if f of A times f of C is negative, then B is equal to C. Okay, then you swap your interval. Otherwise, A is equal to C, and then check for convergence. Just the same way we did with the bisection method. And here's your routine. I call it falsy. Okay. Again, it takes a residual function. Let me fix that. R. There's many more function evaluations in this algorithm. Okay. So falsy takes a residual function, your interval, your bracketing interval A and B, a tolerance, and a maximum number of iterations. Again, like the bisection method, we start with a 0 counter for the number of iterations and with a high error, just because we want to get into the while loop. Okay. And as long as our error is greater than tolerance, which initially it is because we added 100 to the tolerance, and the number of iterations is less than the maximum iterations allowed, then you implement the regular falsy method. Okay. You start by computing the slope m, which is r of b minus r of a over b minus a. And then you guess the root. C is b minus r of b over m. Okay. And then you compute an error, which is the absolute of r of c. Remember, c is your guess for the root. You take it back and you plug it into your residual function. Okay. And that defines your error. Okay. Now you check where your guess is. Is it to the left or to the right of the root? You check r of c times r of a. If it's negative, then b is equal to c. So in other words, your c is to the right of the root. And then otherwise, a is equal to c. Update your iteration counter and move on. This function returns your root, your error, and the number of iterations. Okay? Pretty simple. Let's go back to Python. Okay, and we repeat the same thing. Okay. So you have your Python notebooks up and running. Okay, so this is the falsy algorithm implemented here. I'm going to change F to R. Now notice how many times I'm changing R. I have 1, 2, 3, 4, 5, 6. Every time I call the residual function, that's called a function evaluation. In complex computing, every function evaluation is worth its weight in gold. You want to avoid those like the plague. You want to avoid function evaluations because in compiled codes, those functions could be expensive. They would take the code. If your code is huge, your machine code, the machine language, that's when you compile your code towards the machine language, this has got to find its way in the code to where that function is, move things in memory, plug them in, evaluate, and return. It does it in like faster than the blink of an eye. But when you're doing billions of those functions evaluations, that becomes costly. Okay. So this is an expensive method just by virtue of how many function evaluations we're doing here. But for our intents and purposes, I really don't care about that right now. Okay. But you heard me say the word function evaluation. So just keep that in mind. Okay. And you can be fans who are like, oh, this routine reduces the number of function evaluations, and it'll be very impressive, you know, on your next interview. What did you say, Nathan? Okay. Falsy. All right. So we're going to call it on, what was it? What was our U0? Let's do our U0 at 40 meters per second. and we do R and 10, 20, tolerance 0.1 with 100 maximum iterations. It did it in 2 iterations. Okay, so that was for the mass of 100 kilograms. Let's do the mass of M070, right? The root was 15. So for the same, we had, if we did the bisect, we had R, 10, 20, 0.1, and 100. It did it in 7 iterations. So about twice as many iterations as the regular falsy, okay? All right, pardon me? Oh. Are you evaluating this locally or on the server? On the server, yeah, there's probably some higher demand going on up there. Looks like it killed. Were you able to evaluate this cell? Okay.
Sure, I'll restart it.
That's probably a good idea. They're actually having some maintenance done, so we might lose access to that over the next few days, a little bit. Okay, let's take 5, and then we're going to hit the Newton-Raphson method, okay? And it's going to get more complicated. Pardon me? What's the point slope form?
Like y minus y1 equals m times x minus x1. And then you just give you the same thing. It does in one step. Is that equation okay?
In one shot? Probably. I need to write it down. Yeah.
It'll give you just like instead of like the
in one shot without this many function evaluations. Yeah. Probably. You're probably right. Most likely. But yeah, if you wanna, if you think, if you want to type it up, just send it to me, and then I could incorporate it potentially instead of this. I mean, it's hard. There's different forms sometimes, and it's hard to know which one to teach. Sometimes it's like, oh man, yeah, this is so obvious. And sometimes it's like, no, this is so obfuscating, you know, because it's a trick. So who knows? Okay. We are back. Okay. The next method we're going to discuss is the one and only open domain method that we're going to discuss in this class. And it's called Newton's method, sometimes referred to as Newton-Raphson method, I think. And the idea is to use the information about the function's derivative to guide the choice for the next iteration. Similar to the idea of doing the regular falsy, where we kind of took a slope, right, between the two brackets. But now we're going to extend that idea to, instead of taking the slope of the bracket, just pick one single guess and take the slope at that guess, okay, to improve that guess for the root, okay? But first, we're going to go back to the Taylor series, because the Newton's method is fundamentally just a truncated version. The formula for Newton's method is a truncated version of the Taylor series, and that is going to appear more significantly when we go to multiple nonlinear equations, okay? You'll get multiple Taylor series in multiple dimensions. It gets a lot of fun and interesting. Okay, so given f of x, we've seen this story over and over again. First, we write the full Taylor series around some point x0. X0, we're going to treat that as our initial guess for the root. But forget that for a moment. This is your residual function. Suppose this is your residual function, the function for which you want to find the root. Now we're going to truncate this series by taking, I don't know what Bay is doing there. Probably my son was just kind of got some water and he always starts typing on my computer. So I don't know what I have to review all my proposals and things before I send them out, because there's always some weird text like FJKSLM. All right, so now we're going to truncate this series by only taking the first two terms. So f of x0 and x minus x0, f prime of x0, and we're going to neglect all higher order terms. Why? Because we're going to try and see what happens. Okay, it's numerical methods after all, the art of approximation. Okay, so now we're going to treat this formula. We're going to treat this formula as a representation with an error, but as a representation of our residual function f of x. Here it should be r of x. Pardon me for that. And now we stated things. We make the statement of finding the root of f of x as follows. We wish to solve f of x equals 0. So that's your left-hand side, right? Find x such that f of x equals 0. So go ahead and do that. Treating x0 as a guess for your root f of x equals 0. Develop a formula using this equation, this approximate relation up there. Okay. Develop a formula that improves that x0 guess. Just that makes it, changes it, uses it to make a new guess. Okay. To make a new guess x. Remember, we're finding the value of x that makes f of x equal to 0. Okay. And treat x0 as our initial guess. Use that formula, f of x approximately equal f of x0 plus x minus x0 times f prime of x0. That's you. All right, so we got an answer. Do we have an answer? Nicholas, you got an answer? Okay, so x is, you pulled out x of this equation. You said f of x equals 0, and you pulled out x of that equation. That's correct. Okay, so let's see that. So you simply set f of x equals 0 on the left-hand side, and you just solve for x. Okay, so now solve for x. So when you set 0 over here, everything you know here is unknown except x. Now, because we claimed that this is a erroneous representation of f of x, then if we set f of x equals 0, then the only unknown is going to give us that root x. Okay, so x then becomes x0 minus f of x0 over f prime of x0. Okay. Now, clearly, if you do this one time, it's going to result in a huge error because we grossly misrepresented this function when we took the first two terms of the Taylor series. Okay. However, this could be a recipe to iterate. So what if now we take that new x, x1, call it, and put it back in here? It becomes x1 minus f of x1 over f prime of x1. And call that x2. And then put it back and over again until you converge. And indeed, it does converge if you're not stuck in a local minimum. And so that's Newton's method. Given x0, which is your initial guess, f of x and f prime of x, calculate f of x0, f prime of x0, calculate a new guess for the root, call it x1 equal x0 minus f of x0 f prime of x0, and check for convergence. And then if it's not converged, repeat. Take that new guess and plug it back again and keep repeating. That's the idea of iterative processes. You get a recipe and then you apply it over and over and over again. Okay? Now, in general, we represent Newton's method using an index, xk plus 1, the new iteration, starting with an iteration k, or a guess at k, it could be 0, 10, 15, whatever counter you are. Excuse me. Then the k plus 1 guess is equal to the guess at k minus f xk over f prime of xk. And that's it. That's Newton's method. It only requires 1 point, 1 guess, which is much easier than having to deal with picking a bracket. Okay? Clearly, the closer your guess is to the root, the better. Now, Newton's method has issues, which we will show an example of later. It could get you stuck in a local minimum, and you'll never get out of it. Okay, and then the method diverges. So, Ethan? That's a great question. Do you want to answer that? I think you know the answer. That's like 3 slides down. Okay, but what do you think? You have a function that's very, very complicated that even Mathematica cannot differentiate, or if you differentiate it by hand, you're going to get like 1,000 pages, right? So how would you do differentiation? Maxime, sorry, Michael, you answered 2 questions earlier. Maxime. Yes, we can use a finite difference, right? And that's what we will do. So very good point, Nathan. Very good point. Okay, we'll get to that in a minute, okay? Okay, so here is a Newton method algorithm, the way I would interpret it. I call it Newton, okay? It takes a function or residual function f, its derivative, also a Python function, because we need to evaluate the derivative, right? We need to evaluate that derivative because we need to evaluate the f prime of x0, right? And then an initial guess x0 and a tolerance. That's our error that's allowed. Again, we do the same thing with an iteration counter and an initial error that's higher than your tolerance. And then as long as error is greater than tolerance, iteration less than maximum, you simply compute an improved guess, call it x1, equal x0 minus x0 over df of x0. So those 2 statements here, they take the function names in the arguments, and they go to those functions, they evaluate, they return a value, put it in here, improves the guess, then you reset your guess. You make x0 equal to x1. That's it. You swap the values. And then error, you evaluate your new error, f of x0 or f of x1, increase your iteration, and move on. That's it. That's all there is to that routine. And that's what fsolve is doing. That's what fsolve is doing. I think now we'll be able to show that we get the same answer as fsolve is returning for the same tolerance, okay, because fsolve is doing the same thing. Okay, so now let's go back to our Jupyter notebook and kill the cord. Okay, we go back to our Jupyter notebook. All right, okay, Jupyter notebook. So there's a third activity here called the secant method. Disregard that. I no longer teach the secant method. It's the transitionary method between the regular falsy and the Newton method, but it's not necessary. So you can jump to activity 4, Newton's method with analytical derivatives. Okay. Okay. So Newton, f df x0 tolerance, you just execute that cell. Now, the challenge with Newton's method is you define your residual function, but you also need to define the derivative of your residual function. And that derivative needs to be with respect to the unknown that you're solving for. So our residual function, we wrote it with the expectation of finding the root c, the drag coefficient. So our derivative needs to be with respect to that drag coefficient, not u, not t, not m, not gravity. Okay, only c. And that's why I compute dr by dc. Okay, that's my definition of the derivative of the residual function. So be careful of that. You might have functions with multiple variables and parameters, and you might be fixing all other variables, treating them as parameters except one. In your residual derivative, you only differentiate with respect to the variable for which you want to find the root. Okay, so in this case, it's the drag coefficient, and if you run the derivative in Mathematica, it gives you this. Okay, minus mg over c squared plus this thing. It's annoying, you know. Nathan said it, like, I don't want to do this. So we're going to figure out a way to not do this, okay, because we don't want to do a lot of work. Okay, so now we define our derivative, our residual derivative, df of c. Again, it needs gravity and m0 and u0, and I just implement this whole guy over here. Okay, that returns a value, and that's all we need. Okay, so I'm going to define my
We can see your
df
screen, Professor.
derivative. And now we can go back to this problem. Let's start with the 40 meters per second and the m0 equals 70. Okay, Newton, what do we do with Newton? We're going to call the function, we designed it in a way such that we give it our residual function, our df. Remember, our r was defined way up top. If you restarted your notebook, make sure you reevaluate all the other cells. And we're going to start at an x0 of 10. Let's say with this tolerance of 0.1. Boom, 6 iterations, it gave us 15.177. If we were to use fsolve, okay, and give it the residual function, okay, r and an x0 of 10, let me see what, so its default tolerance is 10 to the minus 8, okay?
Professor
So
Saad, could you
let's
show
run
your-
it, gave us 15.21. So let's do the same tolerance over here. Look at that.
We can't see what you're doing on Zoom.
15.2140891 because it's rounded. Okay, it's the same method, same exact method.
Hello,
Same thing. Okay. Now fsolve
Professor.
did not take a df derivative. You could provide it. So if you look at the
I can
arguments,
see the screen. Hello.
there's something here called f prime. Okay. So you could provide the Newton, the fsolve, with an analytical formula for the derivative, but it doesn't need one. So how is it evaluating it? Exactly what Maxime said. It's using a finite difference formula to compute the derivative so that you don't have to pass an analytical derivative. That's really great because then your routines become much simpler. You know, you only need the residual function. You don't need anything else. Okay, so let's see how that works. Okay, what about the
Professor.
derivative in Newton's method? It's we kind of jump the gun here, but it is sometimes cumbersome to analytically find the derivatives of these complicated functions. And these functions can be really annoying, you know, the exponentials and logs, and like, I don't want to, you don't even want to program it because there's like so many nested functions in there. Okay, so now using that was an activity, you know, which we just did. Using our knowledge of numerical methods, we can circumvent computing a derivative. Remember, we need to know r, the residual function. That's a given. But at least with r, we can compute a numerical derivative without having to do an analytical derivative. So we're going to use the finite difference method. That's kind of how, you know, how nice things kind of fall in place, right? We can use any one of the approximations we looked at to define the first derivative, okay? Whether forward differencing, backward differencing, or central differencing, okay? And this is really just the definition of rise over run, okay? Now I have this delta over here that's spacing, okay? There's no spacing defined. I mentioned that last time. There's no spacing defined for analytical functions. So you can arbitrarily choose that delta, whatever you want. 0.1, 10 to the minus 4, very small number, okay? Clearly, the smaller it is, the more accurate it's going to be, but you cannot take it, absolutely to 0. Okay, I'll show you what I use in the code. Now, I do have a question over here. So what are the advantages and disadvantages of these different approximations? And I alluded to that a few minutes ago. Told you how you can impress your interviewer by saying the word function evaluation. So keep that in mind and think of these 3 methods. Which one is going to be cheaper? Clearly, this one is going to be more accurate, but for very small deltas, it's splitting hairs. But in terms of function evaluations, you might think that they all have like 2 function evaluations at the top, right? F of x and f of x plus delta, right? Think about it. We already have to, in the Newton method, you already have to evaluate f of x. Lucia, yeah? Sorry, would you, oh, they cannot see what's going on? Okay. Well, thank you for letting me know.
Can you hear us, Professor? No.
Oh, sorry, guys, I wasn't hearing you. For some reason, it muted the laptop. Okay, let me share the screen.
Yeah, we haven't been able to hear or see what you've been doing for the last 5 minutes.
Okay. I apologize about that. We've been doing a lot of fun activities. So we were talking, we did the example for the Newton method in the last 5 minutes. We did the example of the Newton method in the Python code with gaps. So this lecture is recorded, thankfully, so you'll be able to kind of catch up on those 5 minutes, but nothing that big of a deal. What's the big deal here is looking at the derivative, okay, of a Newton's method. And oftentimes I argued that oftentimes you don't want to compute a derivative analytically because those can be cumbersome, programmatically problematic. 1 second. And we suggested that we use finite difference methods to evaluate those derivatives, given by any one of those formulas, okay, forward, backward, or central differencing, which we learned in the last chapter. And now I ask the question, what are the advantages and disadvantages of each of these approaches? And I mentioned, the function evaluation idea. Now we should be back in sync. Thank you, Lucia. Maxime, have an answer? No. Yes.
I'm just wondering if instead of f(x) plus delta and f(x) minus delta, that additional step, so it takes longer to do those in the first two.
Okay, so I'm going to claim that this one is going to be more expensive than the others. Although at face value, each one has 2 function evaluations in the numerator. However, in the Newton method, we have x0 minus f of x over f prime. And f of x is already evaluated. So really, with the forward and backward, we already have f of x evaluated. So we're only doing 1 function evaluation instead of 2. Now, that's splitting hairs for a problem like we're doing. But when you have 1 billion times you're calling this routine, it's going to be a big deal. Okay? All right. Okay, so here is the routine with a numerical evaluation of the derivative. Okay, a hint for choosing delta. You kind of want to. This is one formula that I always use for delta. Is you kind of want it to scale with x0 with your guess. If your guess is huge or small, you kind of want it to scale with that guess and add a little perturbation to it. So I do like 10 to the minus 4 x naught plus 10 to the minus 12. Just add a little perturbation to it. It's really not a huge deal, but you don't want your x naught, your h to be lost, or your delta to be lost in the noise with respect to x0. Okay, so you don't want it to be to go as round off and not be visible by your computer. So if x0 is a very small number or a very large number, and you add to it a very small perturbation, your computer might not see this at all. So your h, your spacing, needs to scale with your x0, okay? So that it shows up. You know, when I do 10 to the minus 4 x0, it's kind of, I'm adding perturbation to the fourth decimal, to the fourth point after the decimal point, right? So it is going to be visible as a legible number in the computer, okay? And then that's just the formula. df, f of x forward difference, f of x plus h minus f of x0 over h, okay? And then x1 is x0 minus f of x0 over df. Now, you see this f of x0, you could evaluate it once and save it as fx0, okay, as a variable, right? You can evaluate it once, and then you don't have to have multiple function evaluations. But, you know, for what we care about here, it's not going to be a big deal, okay? So now we can go back to the notebook. Let's do this activity before I let you go. Let's just go back to the notebook and do activity number 5, okay? And call that Newton 2. And look at that. Our new routine only takes the residual function, an initial guess, and a tolerance, which is great. No need to worry about analytical derivatives, okay? So for Newton, we can do, give it R, and then, so let's remember, where were we? U0 was 40, and M0 was 70, right? So that should give us a drag coefficient of about 15. And we're going to start at x0 equal 10, and tolerance 1e to the minus 8. And look at that. 15.21408981, just like the other ones, okay? Okay. Do you have one more minute? For me, I'll show you a demo of how the Newton method works so that we don't have to do it next time. Okay. Let me show you a cool demo. Okay. Newton demo. Let's see if this is going to work. Huh. Okay. Move. Okay, so this is called Newton demo. Okay. So let's see. We should have an iterate button. Okay, so what I'm showing here is a function that shows you how the Newton method operates. Okay. Well, actually, I started with a bad guess. Let me try another guess. Okay, let me try. I'm going to show you an example actually of how the Newton method fails. Okay, and I have to restart this. Okay. Boom, boom. Uh-oh, I picked the wrong number again. Apologize. I'll just show you how the Newton method fails. Okay. 10, 10. Okay, so we're going to do x0 minus 2. Okay. Okay, where's the iterate? I promise I'm going to be there. Okay. All right. So this is a function that I concocted. Okay, it has a root over here. Okay, it has a root over here, but I'm starting my initial guess over there. Now, I mentioned that Newton's method fails in local min if your initial guess happens to be in a local minimum, and this is the case. What we're going to see now is just going to oscillate and stay and never climb away from the minimum. Okay, so actually, sorry, my initial guess is over here. So the slope, that's the slope, okay, at that point, okay, for Newton's method, and then it's going to find that intersection point over here. Okay, that Newton's method is an elaborated secant method, okay? Elaborated regular falsy method. So now we're going to iterate. Okay, now this was our new guess and the slope, and that's our new guess. Okay, so it's going to keep iterating. Look at that. It's just going to oscillate, and it will never converge to the root. Yep, it's never going to converge to the root. The only way to get out of this is to be outside of a local minimum. Okay, so any point over here is going to drive you to that route. Okay, and I just want to show you this. Thank you so much. See you next Tuesday. We'll come prepared for the exam, please. We're going to talk about exam 2 next Tuesday. Okay, so make sure you come in. Thank you so much. Have a nice weekend.